dying for the water, I would have been on time.
Yeah, we're starting early.
What?
We should update that.
Yeah. We have like a Culligan machine in there. It's much less stress than the water. Yeah, we're learning today. I know, it's going to be surprising. I don't know what you said, but yeah. Okay, so we've been enjoying some crystal field theory, some transition metal chemistry, chapter 13. Those would all be different ways of saying it. And so I wanted to go back in time for a minute to chapter 8, because I think that was everyone's favorite chapter. That would be acids and bases.
Wait, really?
Yeah.
Unironic?
That's serious.
Got to throw them in there.
And I want to look at the material HCl. What do you know about it? It's an acid. What kind of an acid is it? It's a strong acid. Strong acid means that it dissociates completely in water, and so you might be inclined to write like this.
Who's this? Is it you?
Or you might be inclined, to write like that. Is that fair? The top one for me is the Arrhenius definition of an acid. The Arrhenius definition of an acid talks something about how an acid has to have a proton that it can donate. And so in that top definition, you can really see that proton. Again, that's just an H+ ion that's free in solution. Upon erasing, I wrote both of these as yield zeros because I'm not a total loser. That means that it's a strong acid or that it dissociates completely, so I think I got that right. But in the second version, instead of seeing an Arrhenius definition, do you see a different person's definition or persons? We haven't learned Lewis yet. Love you both. So hopefully here you see Bronsted-Lowry definition. The Bronsted-Lowry definition says that HCl is going to donate a proton. The water is going to accept a proton. And so that makes HCl an acid. Anything that's a proton donor. We had the same thought, I just really ambulate.
Oh, okay.
I don't know what that did, but it shut it up.
It'll come back on in
Don't
2
try to
minutes.
call me, it may not work.
It'll come on in 2 minutes.
Press the headphone button if it gets too irritating on me. We can tag team it. And we said that H2O was a base because it's a proton acceptor. We similarly said over here that Cl- could be considered a really, really weak conjugate base, and that hydronium would be a nice, normal conjugate acid. We talked something about how the stronger the acid, the weaker its conjugate base. There's actually a relationship said that the product of those two things was Kw. Ka times Kb is equal to Kw.
Interesting.
I'm going to call you like Nomeo today. Because of your pointy little head. So today is the day that we come up with our third and final definition of acids and bases, and that is the Lewis definition of acids and bases. Instead of talking about proton donors and proton acceptors, what we're going to speak about is acids are electron pair acceptors. What happens when Emma doesn't write pair?
Get nothing.
She gets nothing. And we're going to talk about Lewis bases, of course, as electron pair donors. And to see that in action, you could do a reaction where you took something like ammonia. And you might remember that ammonia was kind of a difficult base to understand because it didn't even have a hydroxide. So like as far as Arrhenius was concerned, this wasn't really a base at all. But ammonia does have what we'll call a cute lone pair. Cute little lone pair. And what is the ammonia going to become if you think about its conjugate acid? It's going to become ammonium ion. this could just be seen as the formation of a coordinate covalent bond between the ammonia and the H+. A coordinate covalent bond is a bond where one guy, ammonia, donates both electrons to the bond. So if you were to take the base ammonia and mix it with the acid, say HCl or just any acid you have in mind, what you're really doing is you are having the ammonia donate its electrons to the H+. It is behaving as a Lewis base, and the H+ is behaving as a Lewis acid. You might recall from chapter 3 that we marched across period 3 of the periodic table. And we talked about the acid-base behavior of the different substances we came across. So we had sodium oxide, magnesium oxide, aluminum oxide. I don't know, suddenly this doesn't feel like the right thing. I don't care. I'm going across the table. I just lost interest, as many of you did, in writing them down. I will regain interest. Whew, interest.
PSCOAO.
Argon doesn't form one. Okay, so that's as interested as I'm going to be. What do you remember about the acid-base behavior of these things as we went from left to right in the periodic table?
More acidic.
That's right, they become more acidic. So if you put sodium oxide into water, you might recall that you make sodium hydroxide. And if you put magnesium oxide into water, you might recall that you make magnesium hydroxide. And sodium hydroxide is a strong base, and magnesium hydroxide is a strongish base. I don't think it quite makes the strong mark. I think it's a little bit too insoluble. And on the other side, you might recall that you might make Cl2O7, ooh, some juicy perchloric acid. That's one of the strong acids that your colleagues in AP chemistry would know is strong, but you guys don't know. You do not need this reaction as far as I recall, but you do need the two above it. Do you remember what SO3 makes? That's some strong addition. And this guy, do you remember?
I know this already, but not the name.
Phosphoric.
Yeah.
And I need to balance this. Phosphoric acid, strong or weak?
And then
Any of the possibles. We have 3 strong acids in IB chemistry.
nitric acid,
We're not done, we're not there.
HCl.
HCl, HNO3, and H2SO4, the 3 we've memorized. This is not a strong acid, it is a weak acid. It is quite acidic, and please don't put your fingers in it. And anyone who is doing titrations with iron, this would be my girl Nicole in the other class at the least. They're gonna use 85% phosphoric acid, and that will put a hole right through your finger. So, again, strong and weak does not determine the safety of it. It's just a straight definition as to whether or not we're using a yield zero or an equilibrium arrow. What happens to aluminum and silicon in water? No, it's back to chapter 3. This is glorious, right? Every opportunity to revise,
I really did not
Amarachi.
like this chapter.
You didn't like this chapter?
Not at all.
I know that aluminum is an amphoteric.
Aluminum is amphoteric. It was a right pain in the butt, right?
Yeah.
And so if we took this class before 2016, we had to memorize the 2 reactions to prove that it was amphoteric. In one, we reacted it with HCl, and the other, we reacted it with NaOH, and we saw the products. And silicon dioxide is just slightly acidic. But this is a little bit of a lie. So Amarachi knows the end of the story, that this is a complete trend, but she missed a step in the story that I think would be important if when we're trying to write this on a test. It says amphoteric and slightly acidic. Slightly. I got, a pile to throw away today. I'm just gonna keep putting them in the bin until we find one that works. So where would I find silicon dioxide in this world? Sand, glass, quartz. This stuff does not dissolve in water. Where would I find alumina in this world? We talked about it last time. Alumina, not aluminum, you silly girl. Alumina, that's how we call that. You can call it aluminum trioxide if you want.
Oh, and like
Gems?
Yes, we talked about gems last time. That's carborundum. That is what is at the heart of the gem is the aluminum oxide. Then we put in some impurities, a lot of iron or chromium, and that's what made your rubies and stuff. So the piece that we left out was that these are insoluble in water. So that's why I didn't write their reaction the same way that I wrote the others, because if you put them in water, nothing happens. To make some things happen here, we have to mix them with acids and bases. For example, I think we did something like if you took sodium hydroxide and you mixed it with sand and it was concentrated enough, you could make sodium hydrogen silicate. And because you produced a salt, you knew that if this was a base, this had to be an acid. So we could say that silicon was somewhat acidic if it had to choose, but on the whole, it was pretty hard to prove that. Sometimes things take a weird turn. I was trying to convince you that aluminum was a good Lewis acid. So now I have to imagine a kind of different scenario. Or I guess you have to imagine if I put Na plus in water, let's say in the form of sodium chloride, what would the pH be?
salt.
Yes, salts, table salt. I'm putting NaCl in water.
So salt water.
I have made salt water. I'm asking the pH. Like it was in my head, it's just poorly written.
At room temperature?
Room temperature, good question.
Below 7.
And Audrey is saying that sodium is the conjugate acid if she has to, the sodium hydroxide. Sodium hydroxide is a strong base, so Na plus has no ability to change the pH of water, and Cl minus is the conjugate base to hydrochloric acid, a strong acid, so it also has no ability to change the pH of water. So you might recall that I could go through Aditi's notes and I could find like a little bubble, and she would say that there were some ions she knew that never changed the pH of water. And they were exactly related to the strong acids and strong bases that she was just listing off. So hydrochloric acid is one of the strong acids we memorized, so we put chloride in this list. Nitric acid is one of the strong acids that we memorized, so we put nitrate in this list. Again, the idea is that if this reaction goes to completion, that the reverse doesn't happen. And so there is no appreciable amount of Cl minus that will turn into HCl. It is a crap base. Those 7 things don't change the pH of water. Am I making this up?
Is that the negligible stuff we talked about?
But can you explain why they don't change the pH of water reactor?
So if we know that when you put HCl into water, we treat this as essentially a yields reaction to make Cl minus and H3O plus. Are you comfortable with everything that's on the board so far? Shit, she's already whispering. Okay, so I have written it as a Bronsted-Lowry because I felt good about it. I think that it's the same one that's on the center board that you didn't have a fit about, so I feel okay. I am now admitting that every time I write a yields arrow, there's really some sort of an equilibrium, but the equilibrium is so heavily product favored that I write it differently. And so I'm saying this K, this equilibrium constant, is a whole lot bigger than 1 because it's so very product favored. I feel like I'm taking my general's exam. That's the exam you take to get candidacy for your PhD. You just in a room with some professors, they can ask you any questions you want. Like, here we are. Like, okay, I think I can explain this, Audrey. Whew. Now I want to imagine what would happen if I took Cl minus and I added it to water, and it actually did change the pH of water. It did behave as a base. So I don't believe this reaction happens appreciably. That's why I put the first question mark. The second question marks are because I have to calculate some sort of a K to convince you of this, I presume. So what I'm going to do is I'm going to add these two reactions together. And I'm going to cancel things that appear on both sides. So the HCl would cancel the HCl. The Cl minus would cancel the Cl minus. And lo and behold, I would be at water can auto-ionize to form hydronium and hydroxide. And the K is 1 times 10 to the minus 14th. Or 1 in about every 10 million particles would do that.
You said appreciably, what does that mean? Like,
In an amount that is meaningful to me.
okay.
Is anything weird here yet? So what's the value of the equilibrium constant that Audrey wants, the Kb for chloride? This is the Ka for HCl. We know that Ka times Kb is equal to Kw. So we know that 1 times 10 to the minus 14th is equal to a number that is bigger than 1. It's around 1,000 times the Kb that Audrey is challenging me with. And so the Kb is going to be significantly smaller. Let's make this up. So Kb would be 10 to the minus 9. That doesn't seem good.
11, she said. 17, 17.
I was doing the next calculation, I apologize. I was trying to take square root and I got an odd number and then I got an even number. I liked the even number better. So this is why I don't think that reaction matters. This is why I don't think chloride can be a base. Because the more this happens, the less this happens. And so if I can identify this as a strong base, I can identify this as something that has, if I can identify this as a strong acid, I can identify this as something that has essentially no base character. And so if I were a better person, I would continue this farce and try to convince you that the amount of hydroxide that I am making in this reaction is less than just the autoionization of water. So like the hydroxide that is naturally in water, if you will, is a bigger number than this. So it just doesn't happen. It's actually going to inhibit this.
This is why those don't change.
Yes, this is why those don't change the pH. So that was like a long, kind of terrifying exam question about why they don't change the pH.
If we have, like, if that was a question, like,
Do we need to be able to do this?
You need to,
like, if
okay,
if
things
there
you
was-
need to know in this story. The bubble note that Aditi has in her notes, she needs to know that because you get questions like, hey Amarachi, I have a pile of sodium cyanide. What will the pH of a solution be? And Aditi's gonna say sodium doesn't affect it, cyanide, not in my list, negatively charged, gonna be basic. So that was something we learned how to do in chapter 18 when we learned about the pH of salts. We just crossed out the 5 things that we knew. If we had cations left over acid, if we had anions left over base. If we had nothing left over neutral. So it wasn't, nothing's easy. But like there was no math in that story, right? We just crossed out the things we knew didn't matter. And again, if it was positive, left over acidic. If it was negative, left over basic. Nothing left over neutral.
If we were asked,
You
like,
also do need to know this relationship. I believe that relationship is likely in the data booklet. Mohab agrees that it's probably there. But we used that in a different context. It wasn't to prove this. The context that we had to use that in was acetic acid, or ethanoic acid as y'all would call it, has a pKa of 4.76. You have a 0.1 molar solution of sodium acetate or ethanoate. What is the pH? So you needed to use the relationship that I used to solve this problem, but this is a once in every several years problem. This is not a common problem. It's not a problem I think any of you enjoy. What is the pH of a 0.1 molar solution of a sodium ethanoate solution? Do you remember this? Are we gonna do this problem?
Is it like the rice table that we made?
Yeah, we're gonna make a rice table.
Oh, yeah.
Yeah. Yeah, there's some X's.
Rice table.
Yeah, it was a rice table problem.
If we were asked, like, why doesn't Cl affect the pH of water, would we have to draw that?
You would not be asked that question. Again, I think you need the bubble note that says Cl minus does not affect the pH of water, and your one sentence response would be because its conjugate acid is strong. So no math, you would just say like the conjugate acid is strong, this is, clear. Am I doing this problem or not? I don't have to do anything, I'm trying to talk about chapter 3.
Oh, so wait, are you asking me to do the problem?
I'm asked, so she wants me to do it.
Yeah. Will it help you check?
Not at all. Like it is rabbit hole.
I mean, it would be nice.
Yeah, it's just like quick review.
Yeah. Because I don't remember.
Okay, so sodium ethanoate is made up of two things, sodium and ethanoate. And all sodium salts are completely soluble. So I'm just gonna ignore the sodium because I know it doesn't affect the pH. So all I'm worried about here is that I have a 0.1 molar solution of this stuff. Have I done anything crazy yet? Now that's only negatively charged. I was trying to convince you that that meant that you knew if this was an acid or a base. It's a base, and so I'm gonna write down the equation for a base reacting with water to form its conjugate acid. I'm gonna write it the right way. And hydroxide. That reaction is defined as base hydrolysis and given the cute nickname KB, like some of your large mammals. Let's never call it a cute nickname again. Given the very imposing nickname KB. But I was told something about the pKa of its conjugate acid. How do I get from a pKa to a Ka?
Subtract that from 14.
Okay. If I took 14 minus 4.76, I would have the pKb. That would be 9.24. And I heard 10 to the? Okay, this is 10 to the minus 9.24. And it's going to be on the order of 5 point something times 10 to the minus 10. Anyone who wants to calculate is free to calculate.
Now we can find out.
What?
You have your 2 6 instead of 2.
Well, I was thinking about this 6. In an effort to be less late than Margaret thought I would be, I didn't bring them back. I'm gonna hit an orange button. I don't even know how to hit a shift. 10 to the minus 9.24. 5.8. Okay, so you guys promised me a rice table. We have R. What do I put in the I row of a rice table? R stood for reaction. What does I stand for? Initial. So initially, all I have of interest is 0.1 molar this stuff. You don't have anything else. The change is gonna be that some of this is gonna go away, and some of its conjugate acid and hydroxide are gonna be formed, such that at equilibrium, I have less of the base, and I've made some conjugate acid and some hydroxide. So the equilibrium constant, K, should be equal to x squared over 0.1 minus x, but it's also equal to 5.8 times 10 to the minus 10. So I make an approximation, because I'm too scared to use my calculator. You think they'll get rid of that with the new syllabus? Would that not be exciting? If we could like actually calculate?
What? In chem, we're not allowed to do
You're allowed to use a calculator, but we make an approximation in this that you, calculator goddess, do not need to make. You have skills on your calculator.
Oh, yeah, X is.
We make the approximation that this is negligible compared to 0.1, so that we don't have to solve the true quadratic, we just have to solve a x squared equals a number quadratic. I don't know the binomials, I have a trinomial. Help me out, math teacher.
It's just a,
An easy one instead of a hard one.
yeah.
One I can do on this calculator I don't know how to use.
Looks more like a parabola than a wonky parabola with asymptotes.
I think they both look like parabolas.
Yeah, but one's more wonky.
Like a normal parabola instead of a wonky one, it's like asymptotic.
What?
So that one's gonna have an asymptote at 0.
Asymptote?
Yeah. It's gonna be
Oh,
a,
the line below it. The line where
it's gonna have, it's gonna do this. It's gonna do this.
Like if the asymptote is like the origin, it's
What?
never gonna.
It's a quadratic.
Well, if
There we go.
when you get rid of the minus x, yes, it's just a normal quadratic. But when you have the minus x,
Yeah, it does.
it wonks it over.
When I get rid of the x, I make it centered on the y-axis. With the
Yeah.
x, I have a h and a k.
All I'm saying
It's
is,
still a quadratic, it's
I
still
get it.
facing up.
yes. But
It is
when
no
you-
wonky, and a quadratic doesn't have asymptotes.
It does when you put a 1 over x. When you have a 1 over x,
Dude, there's no 1 over x
you
here.
got rid of it, yes.
Can we pull decimals?
But if you keep it
One over X is just X on the denominator.
He's telling you boo-boo.
I
Like,
might be telling you boo boo.
Wait, what were you
What is the
Why
essence?
are we doing that?
we don't even need decimals.
So if you put it, like you have like an x squared
Like,
plus
some of
1
you
over
are
x.
solving 0.1k minus
Something
kx minus
like
x
that.
squared equals 0.
1 over.
And some of you are solving 0.1k minus x squared equals 0.
He's right.
How is he
It
right?
looks like this.
It turns really disgusting.
That's what it looks like with the minus x.
That's not the...
Yeah, it
That's the exact one.
Okay, but we're not solving that. So you're
True,
saying
True.
It looks like this without.
this isn't a parabola.
is. Not the shape of these. Parabolas pertain to the shape.
Okay,
of the
so
function.
what Amarachi and I weren't fighting about, because she's a calculator goddess, is that she had to solve a quadratic to get the value for x. This is the quadratic that we are solving. Ain't nobody looking for the functional form on the right-hand side there. Ain't nobody
Wait, how
care.
did we get there then? How did we get to the point where?
Discussion.
Like, that's just not even part of the discussion.
Oh, it
Like,
isn't.
we're now saying, we have solved some algebra, the right side of our equation, ooh, we could plot it.
Yeah.
But we're just caring where k crosses it. It crosses it at some point.
Don't need to plot it.
How did we get to this?
No.
I'm lost.
Wait, what is the argument?
What are we doing now?
Oh, so you're saying
Sorry.
that we plotted to solve to find the solution?
I was thinking.
And then you were trying to.
Can we just
We're
like-
solving for x. The IB way of solving for x is solving this expression because it's very easy. Amarachi plugs into her calculator x equals the square root of 0.1k and takes the positive root because these have physical meanings.
You can keep it like that.
She's done.
Yeah.
Her calculator will solve this quadratic as well, give her 2 roots. She'll still choose the positive one because it's still a physical quantity. Okay. So x is equal to 5.8 times 10 to the minus 11 square rooted. That would be 58 times 10 to the minus 12, which is about 8 times 10 to the minus 6. Give or take. 7.6? Thank you. What's the pH of this solution?
Negative log of
If I was to take minus the log of x, I would get,
negative log
the negative log of that.
of, yeah.
See, if that were a 10, I would get 5, but it's not a 10. So I'm gonna get 5 point something. So I'd like you to think about if you're right. 5 point what? I'm gonna keep her. She's my favorite. So Mohab, why are you wrong? Mohab told me this is the pH.
It's not the P, that's the P.
Oh wait, that's the
something else.
PKB. POH.
Yeah, because we did it with PKB.
Yeah.
Oh. Oh, what a pretty answer.
Wow.
8.888. Is that an angel number?
Perhaps.
It's been a long time.
Oh boy.
This was my favorite.
It's a sign. My time is
Is this even an equilibrium or acid?
This would be chapter 18.1, probably, .2. It's definitely acids and bases. So we're applying equilibrium, which we learned in 7, to acids and bases, which we didn't know them.
This is my least favorite unit.
Yeah,
Honestly,
blame Emma.
I didn't
But
like
the P,
mechanics.
no, it's not, but the kinetics was the worst. The P, liquid.
We didn't really do much.
The what was fun? Oh, the pink liquid? Phenolphthalein? Phenolphthalein?
That was I think the most enjoyable part. Yeah. That was, it was like a little spike of fun. Yeah, and then we fell off the peak. That was really high.
I was ready to complete the square, people. I was ready to find H and K. Were you not ready to complete the square?
I forgot how to go.
I was ready. I was ready. Okay. So sodium in water. What do you think about magnesium or aluminum in water?
They want dissolve, or at least aluminum.
So the aluminum oxide won't dissolve, the magnesium oxide won't dissolve, but I'm gonna take salts. I'm gonna take magnesium sulfate, some nice Epsom salt soap, or aluminum nitrate
Epsom salt is magnesium.
sulfate.
What? Where's Epsom?
pH is less than 7. Ooh, but these don't have any H pluses and they don't have any OH minuses, and they seem to have affected the pH of the water. How did they do this?
Oh, because they're cations? They're both in solid. Yeah.
So what Audrey is suggesting is that the aluminum will actually form some interactions with the water. It can actually form a little bit of a bond, a coordinate covalent bond, if you want. And on occasion, the oxygen will actually give up the H as an H plus. Oop, wrong way. And you will get small quantities of aluminum, 5 waters, 1 hydroxide, an overall 2 plus charge. What did I leave out? Purposefully. And a little bit of H plus. And that's why Karthika told you that this solution will have a pH that's less than 7. Maybe 5, maybe 6. It won't be super acidic. But because aluminum acts as a Lewis acid, it can make this coordinate covalent bond, or the oxygen lone pair can be donated to the aluminum. As a consequence of that, you make small amounts of this, but enough of it that you will change the pH of water. You will lower it. This is a Lewis acid, Lewis base reaction. We still measure the pH by looking at the concentration of H+, so we have to affect it. But this itself just acted as a Lewis acid. That's why it affected it. So if we're talking about transition metal chemistry, what are our Lewis acids? All of the transition metal cations. Name any of them. And what are our Lewis bases? Water. And any of the other ligands we were putting on. All of the reactions we talked about were Lewis acid, Lewis base reactions. Bonjour, ça va? Of course. Bien sûr. He walked with Greece. That was really exciting. I'm done with Lewis acids and Lewis bases forever. If you want to feel like you understand this, you're going to check out section 8. I'm looking because I got nervous. Is Ruff good?
Taking limited snaps because his body is not able to take it. And he can wrap every step, pretty much.
18.1.
This is 18.1.
This is 18.1. 18.1 in the book you don't use is 1.5 pages long. So what you need to know is a Lewis acid is a
Electron acceptor.
an electron pair acceptor. Electron pair acceptor. And so how would I find one in a multiple choice question? What would I be looking for?
Transition metal.
I'd be looking for a metal cation. I'd be looking for something that could take a lone pair of electrons. Let me give you one more example that's going to be in 18.3, but not relevant to us in chapter 13, and that's going to be an electron deficient compound. How many electrons are around boron? Chapter 4. 6, because it's part of Babel. Beryllium, boron, and aluminum are 3 electron deficient compounds. When we make boron trifluoride, B-ball. B-E-B-A-L.
So there are no lone pairs on the boron.
These are the 3 electron deficient compounds.
The atoms that make them, yeah. That is the Lewis structure of BF3. Do you notice that it's electron deficient? It doesn't have an octet, that's right. So boron is one of the ones that will violate the octet rule. But boron will make a complex with ammonia. That complex, known as an adduct sometimes, is a coordinate covalent bond between the lone pair on nitrogen and the electron deficient boron. What is the acid in that reaction?
The boron.
The boron trifluoride is an acid, it's an electron pair acceptor. What is the base? Ammonia. That feels good because I know ammonia is a base. And the product is that coordinate covalent bond. Most of the questions about Lewis acids and bases are multiple choice questions. You know everything you need to know. That was really exciting. So let me show you one of these beautiful transition metal complexes again. chlorocobaltate 3? Or that thing.
Hexa.
So how many chlorines are there?
Hexa.
What is the shape around the cobalt?
Tetrahedral.
Octahedral.
Sorry.
What is the charge on a chloride ligand? Chloride. Same chloride that was in sodium chloride. So what is the charge on cobalt?
3.
So this ends cobaltate because chemistry sucks. 3. Cobaltate because it's negative. It's got a negative charge, so we say cobaltate. What is this 3 in Roman numerals?
Like
It is the charge on the cobalt. It is the charge on the cobalt. So that's stock notation. So you probably remember from iron that you could make FeO and you could make Fe2O3, and you couldn't call them both iron oxides, so somehow you needed to decide which was which. And you said oxygen has a typical charge of, and so this is +2 iron, so this is iron 2 oxide. Oxygen still has a typical charge of -2. You have 2 irons. They must be iron 3 oxide. Is that reminiscent from chemistry? Super dull. I don't enjoy nomenclature. I don't enjoy it. I'm good at it, but I don't enjoy it. Okay. How many D electrons does cobalt have?
You start at scandium or?
Start at scandium.
1, 2, yeah, 7. Or is it a weird one or no?
Okay, so that's the neutral cobalt, but you guys told me this cobalt was +3. So how many D electrons does this cobalt have? It's the answer I expected.
How did you do that?
No, don't, I was just like, you were sure, and they're like, yes, I'm like, okay. So to get the D electrons for cobalt 3, remember we remove from the 4s first, and then we take the last one from here, and so this would have an electron configuration 3d6. Now we put this into a octahedral structure, which meant that the d orbitals were split into 2 levels. The lower level, known as the T2G, and the upper level, known as the EG. Now, I chose the ligand chlorine here. Chlorine is a weak field ligand. You have a spectrochemical series around about page 15 in your book. If you feel like you don't know that, it's in your data booklet. So how would it look different if I took cobalt with 3 cyanides, where cyanide is a strong field ligand? Also has a -1 charge, so the cobalt still has 6 electrons. So I haven't changed like the electronic structure of the cobalt, but I feel like I have changed something about this picture, what the cobalt's electrons are doing in a crystal field. She's doing an optimization problem where she has a circle and like a pen inside it or something.
No, it's a box inside of an archway.
So how would this look different? It's a strong field ligand. If you make stronger coordinate covalent bonds into that Lewis acid, how are the d orbitals or the d electrons going to feel about those ligand electrons coming by? They feel bad, and when things feel bad, the good guys get it good and the bad guys got it bad.
Is this
The crystal field splitting energy? I hope so. electrons to put in. And over here in the strong field, I feel confident. I feel 100% sure that these electrons are going to do that. Is everyone okay with that feeling? Over here in the no field, if I just had a cobalt ion by itself, I feel 100% sure about that filling. Everyone cool with that? That's Hund's rule. But here in the middle, I'm not sure. What are my choices? You're just mumbling at me now? Maybe. You're a proud woman in STEM.
So there's always 3, 2, T, 2, G, 1.
The T means 3 and the E means 2.
Because there's X, Y, Z, and then the other weird ones. And so it means the electrons are at different higher level. So some of the electrons in the orbitals are in different orientations.
The orbitals have different shapes or different positions. That would be a better way of saying it. The orbitals that avoid the ligands are lower in energy. And so I'm saying if it's really a good scene, they'll all take that option. But if I took the 6 people here and said, yo, we're going to Disney, the rooms cost $1,000 a piece. How many rooms are we going to get? And suddenly Quinn and Mohab are like, yo, we are besties. Of course we'll room together. No worries. This cost is too high, so they will pair up in rooms. But if it's free to take new rooms, only Emma and Morgan have to be, you know, just a joy.
Joy.
But what if it's like ambiguous? What if the rooms cost $50? Is it worth it? Is it worth it to get the room?
Yeah.
What if they cost $100?
No.
So like there's a clear cutoff point. We have to compare the cost to the pairing energy. Nobody wants to share a room. What does CFSE stand for? I put it on my picture just so it was clear. The delta is the distance in energy between these two choices. The pairing energy is something that I can't show you a picture of, but I think that you can feel in your heart. It's the punishment of having to share space with another person. You guys are so casual about it. If I get these top levels low enough, the pairing energy will eventually be larger than the crystal field splitting energy. We refer to this as a low field, high spin The crystal field splitting energy is small, so many of the electrons are unpaired. Over here, we would refer to this as a high field or a strong field. Maybe I'll use strong and weak. Do you like that better? Could I experimentally tell these apart? Could I experimentally tell these apart? You guys made me do this shitty acid-base problem. Now you're all tired. Jumping jacks? Yoga? What'd you say? What did I agree to? Break? Dude, answer my question. We'll be a step closer. The color would be one way of telling them apart. Good job. This color, what's your best guess?
Blue, red.
Red.
I think orange.
Red.
Red.
Okay, so I'll give you two choices. We're gonna keep this green or red, and we're gonna put a question mark.
Red.
And over here, I was told that the color would be different, so what color are you presuming?
Blue.
Yeah, blue, purple.
Green.
Blue.
She's just saying red over and over.
I think it's blue. Blue or purple? Oh.
Any other choices here?
None of them will up the.
So when this thing is in a lit room, it will absorb white light, visible light.
But none of the
The
other.
light will be resonant with one of these transitions, and so it will absolutely pop up there. So this will appear colored.
But isn't it like pairs?
It doesn't matter, just one of these electrons will pop up. When I'm talking about the pairing, I'm just talking about the ground state electron configuration, what is the cheapest way. So this doesn't mean that if we get you guys into rooms, you're not gonna visit each other. Okay. Could you tell me what colors you're screaming out mean? Is that the color I see?
When you like goes up.
Like when you say I'm gonna see different colors, I was told I was gonna tell them apart by color. You're telling me the color they appear. That's what you guys are screaming?
Oh, the light,
That's
the
the
light
color
is
it's
color.
on.
Okay, so you're telling me the color they absorb. That's hard for me to observe.
Well, isn't
You
it
know, I
the-
observe the color of the solution more
they-
easily.
They reflect.
Okay, so I'm comfortable with opposites, so I got some green or red, so I felt like the room was unsure of which answer they were giving me. That's why I thought I could write them both down. What does this look like to me? What is my observation of this?
Green.
It'll look green.
Okay, it'll look green. We think this distance is very small, so it will absorb the lowest energy red light and appear green. This distance is very big, so what color is it going to absorb?
Like blue.
It's going to absorb blue or violet,
It'll look orange.
and so it's going to look orange or yellow. There's another way you could discriminate between these two molecules, and that is by virtue of their magnetism. If you have no unpaired electrons, you are referred to as diamagnetic. Not magnetic. Diamagnetic things are not magnetic.
I thought it was was not, and die was like,
Dia kind of means opposed, I think, like a diameter. How does dialysis?
I have no idea. I thought words that start with that.
Okay.
Diamond.
diaphragm.
What does Fran mean?
That's
Fram.
I'm not in medical terminology.
Definite opposition there.
Diarrhea. No, but
Take some
diarrhea.
tea.
No, it's like diarrhea. Rhea is flow. Wait, so why would the dia not flow, but diarrhea is flow?
When there's a shorter path to go from T to G to EG, is it a lower energy?
Like gonorrhea.
Like the distance between them is supposed to be proportional to the energy absorbed. So the short distance means low energy and the long distance.
Red's the red side is more lower energy.
So if you're
longer.
absorbing red light, you're going to look like the thing on the left.
So then
On the right is going to be absorbing purple light in my,
on the other side.
yeah. So looking yellow. Okay, the opposite, something that has a net spin, is referred to as paramagnetic. Paramagnetic. It has unpaired electrons. It is paramagnetic. If you want to make a ferromagnet,
Iron.
ferromagnet is a permanent magnet, usually made out of iron. The first thing you need is all of the little irons to be paramagnetic, and then you need them all to point in the same direction. So if you guys were cool, like Margaret, you may have in your life taken a screwdriver and rubbed a magnet on it.
It's like paper clips, yeah.
And they don't know what screwdrivers are.
We know what
I know what a screwdriver is.
They have never held a screwdriver.
I have.
Uh,
I have.
held it. I
Woman in mechanics
held it.
also.
What happens when you do that?
Magnetism.
You briefly magnetize the material there because it is paramagnetic. So you will take each of the little metal ions in her happy screwdriver and you will align them so it will be a permanent magnet. So it will actually hold on to a screw. So your magnetic screwdriver will hold the screw. But the heat in the room will eventually take those little domains and untwist them. So it is no longer net magnetic. But for a short time, with a permanent ferromagnetic, you can magnetize a material that is paramagnetic. So this is like the first step in having a collective process that is being magnetic. So like one atom doesn't make a magnet. It's a collective process. All of the things have to do it together. We don't talk any more than this about magnetism. So let's recap. No unpaired electrons. Diamagnetic. That means you are not magnetic. Unpaired electrons. Paramagnetic. That means you are. Generally speaking, if the levels are close to each other, you will use Hund's rule and you are more likely to be magnetic. If the levels are far away from each other, you'll go back to just straight up alpha. You'll be like, I'll put the electrons where it's cheap. Typically those things will be less magnetic.
Dia means through.
Through.
Para means with or alongside.
Well done. Through. Diameter meter
So
goes
diarrhea
through the
is
circle.
through flow.
Through flow. Through flow.
Flow through.
Feces.
I like Rhea.
Yes.
Is that,
I don't like that it's diarrhea.
change like the thingy? So that's why like the aluminum to one side and aluminum to one side is separation.
So instead of choosing aluminum, choose iron.
Oh.
And yes. So if Audrey wanted to change delta, she can increase, so she's gonna increase it. Just so that we have a way to answer this. So you can do decrease, just give me the opposite of everything she says. She can increase the charge on the metal. Why would that increase delta? I gave you the data last class. I left it on my desk, but at least I filled it out. So delta talks about how close those ligands come in to that Lewis acid metal cation.
So if you're increasing the proximity of the thing.
That's right.
The charge is gonna be higher than
I think the order of those is wrong. So since the charge is higher, those ligands are gonna come in stronger, and so those d orbitals are gonna be more split. So the ligands, remember, they have a lone pair of electrons that they're trying to donate into that metal center. They're gonna be more inclined to donate those electrons to something with a more positive charge. They're just gonna get closer.
You said d orbitals are gonna be more split. And then
More
you-
split.
And you make this.
Increasing delta. So we're gonna come up with 3 ways to more split. Way number 1 is increase the charge on the metal.
And it literally looks like that, or is it just like a? Like
Literally, the energy levels look like that, yes.
Oh,
We're gonna choose a stronger field ligand. So again, we have the spectrochemical series. It tells us that chloride is a pretty sad little ligand. It tells us water is quite in the middle, and it tells us something like cyanide or carbonyl is strong. So if we wanted to increase delta, we could change the ligand. I did that with the copper sulfate. Remember how I took the copper and I put it in water, then I poured in ammonia? Ammonia was a stronger ligand. You'd watch the copper change colors. areas where we understand the splitting, where we have that 3-2 pattern that you're required to memorize, is with octahedral things. They have 6 ligands, but if you looked at tetrahedral compounds, or if you looked at linear compounds, you would find that the splitting is generally smaller because there are only 2 or 4 ligands messing you up instead of 6. So remember, what we're watching is how much the ligands mess with the non-bonding d orbitals. If I have 2 things messing with it, it'll be a strong effect even if I can't draw the picture. If I have 6 things messing with it, I expect it to be a larger effect because there's 6 of them now. There are 6 negative things coming in, so my electrons presumably are going to be more perturbed from their happy, we're all the same state. 3 ways you can change delta. Felt like that was the question, how do we change delta? That's the second most common question you get. What do you think the first most common question you get in this chapter is? Why are transition metals colored?
Because of the aluminum.
Because of the different levels of their d orbital energy, absorbing and
Yeah.
reflecting different wavelengths of light.
The color wheel.
No,
And they
don't
absorb-
just say words. Like actually put them together in a cohesive sentence.
And then they reflect it. And then.
But obviously it has something to do with their nature as transition metals.
Number 1, they have a partially filled d orbital. Remember, scandium-3 and zinc were losers, they were colorless. If we want color, we need to have a partially filled d orbital that is split by the presence of the ligands in the crystal field. That's what made us have 2 energy levels. So that electrons in the T2G can absorb visible light such that the compound appears the complementary color. So they move, they get promoted. Those are the 2 most common questions. Don't worry, I have together some practice for you so you can
So,
Thing that comes off, like a ligament. Things that
So
come.
a ligand is the thing that bonds something to like a metallic thing. Can you explain what a ligand is again?
A ligand is the thing, it's the Lewis base that bonds to the cation. It's like the chlorine or the water, whatever has those 2 electrons that makes the coordinate covalent bonds of the metal. Crystal field.
like, chapter. Like what?
13.
So all of 13.
13 has 2 chapters, 13.1 and 13.2.
Then you go back to part of the
18.1 and 18.
I mean, so Lewis bases and acids are in 18.1, I think I screamed out. I don't know, I told you what it was when I had the book down. Okay,
So, and then the rest of all of this.
13.
In
increasing the charge increase the.
So you are a metal cation, and I am a ligand, and I have 2 electrons that I'm really trying to get as close to you as possible. You also have some d electrons on you that are kind of angry that I'm coming up, right? Because they have a negative charge and I have a negative charge. But if you have a really, really positive charge, then my 2 electrons are going to be like, let's go. And they're going to get as close as possible to you. They're going to be super coulombically attracted, right? But that means that your own non-bonding electrons are going to be extra bad. So you're going to have a bigger split. The ones that directly bump into the ligands are going to be more angry because the ligand got closer because of your big positive charge. If you had a smaller positive charge, then these ligands wouldn't get as close, so your own d orbitals wouldn't be as bad. The last iteration of practice problems went comically. See, I envisioned that it would be homework and then never assigned it as homework, so I'm sure that you did all of those practice problems. Yes, I think no one did. Remember we did 3 in class and then 1 and 2 I left with you? You don't remember this?